In question number 3, you're asked to convert or figure out what the temperature of the center of the sun is by looking at this one reaction. You won't get the right answer, by the way. You're going to get a value that's much higher than the actual center of the sun. There's a number of reasons for that. But the problem posits that in order for the sun to fuse deuterium, and deuterium, you had to look that part up, is hydrogen 2, which is a proton and a neutron. You have to get the two nuclei inside what's called the critical separation distance, which is about 2 femtometers. So you have to get them 2 femtometers apart. Once you get that, you get past what's called the Coulomb repulsion barrier, and the strong nuclear force will take over and will bind the atom together and form helium. This is not how the sun works. The sun works on a different cycle called the proton-proton cycle, although in the proton-proton cycle, there will be a point where deuterium atoms will fuse. You have to create the deuterium first, and that's happening in the sun too. That's where a proton and a proton interact in such a way as to create a proton and a neutron and basically kick off a positron in the process. That creates a deuterium atom. Deuterium atoms are more dense than the hydrogen that's around them. They sink to the center of the sun, and then hopefully deuterium atoms start to hook up later on. It's a complicated procedure in the sun. Now, we don't know how fast the particles had to start in order for them to get close enough for this to take place. But we do know that they have to get to at least 2 femtometers from each other. So we could work this problem backwards. We could assume the 2 particles start off close together and see how fast they're going after they separate and have traveled far enough away for all of their potential energy to be converted to kinetic energy, which is how I would do the problem. We can figure out the amount of electric potential energy between the 2 particles. We have a method for that, probably involving something like Q times the electric potential between the 2. Or the electric potential given off by 1 based on where the other one's going to be. And then we can set that equal to 1/2 mv squared plus 1/2 mv squared for the 2 deuterium atoms. Now, the truth is, this is how much kinetic energy they would have to get this close together. But you're just working the problem backwards. Now, from here, you're just solving for V. And there's a lot to do to solve for V. I mean, for example, you'd have to know the charge of the particles to be able to figure out the electric potential. But that part's not terrible. The charge on the proton is the same as the charge on the electron, so Q is just one of the charges. The electric potential is the electric potential created by the other charge. Q over 4 pi epsilon naught times R. And that has to equal, in this case, mass of the proton plus mass of a neutron times V squared. Got rid of the 1/2 when I add them together. Now, protons and neutrons are very similar in mass. You could use 2 times the mass of a proton and get relatively close. The truth is a deuterium atom is actually slightly less massive than 2 protons, but I wouldn't expect you to look up the mass of a deuterium atom. But you could have. It's slightly less than the mass of 2 protons. And that's because there's binding energy, which reduces the mass. The energy of the mass of the particle goes into the binding of the particle up. But it's not going to change the answer significantly enough to make a difference. This is about form over function, meaning I don't really care what the answer is. You can use this to figure out the velocity of the particle. It's pretty high. You should expect it to be somewhere in a range of 10 to the 6 meters per second, which is slightly relativistic. Now, once you've gotten that, you can figure out that the kinetic energy is equal to 3/2 the Boltzmann constant times the temperature in Kelvin. So you can reverse this to figure out what the temperature is in Kelvin. So once you get the velocity, use it to calculate the kinetic energy of one of the particles and figure out what the temperature is from that. I got a pretty high temperature, higher than the actual center of the sun. Now, part of the reason it's higher than the actual center of the sun is there's a lot of deuterium there. It's very dense. So the particles don't have to be going as fast because they're already tightly packed together. So their vibrational speed and their linear speed is never enough because they're always bouncing into other particles that are around them. So you don't have to get them this fast. This would be two deuterium atoms in space having to be just, happen to, run into each other. That's unlikely to occur, but the center of a star, you have a very dense system. And so the probability of a high energy impact is higher. So, but I'm not here to talk about stars, and I'm not going to engage any questions that have to do with stars after what I just said. So if that's your question, put your hand down. Yes, sir?
Can you use from infinity to 0?
That is what we're using here. That's where this relationship comes from. The assumption was that we started at infinity to get this relationship. Okay? Jeremy?
Can you do number...
Are all questions about number 3 done? Okay. All right, we're almost done on time. Good with that. Go.
Number 8.
I can do it. I guess the real question is, can you do it? Jeremy, what is an expression for the electric field when R is greater than R?
That's just going to be, the electric field is going to be the charge over the separation distance squared times 1/4 pi.
Now, what is the electric field for R less than R?
I forgot who that one was, so you didn't, and I think it was wrong. Because
It's in your notes.
yeah, but I didn't. Got Q over the total radius of the sphere to the 5th power times 1/4 pi epsilon naught times little r cubed.
No. It's linear. This is it. And these two functions become the same function when R equals R. That was the whole big thing I made in class about that. I would, if you don't know where this came from, I would redo it. Gauss's law. It's on the exam about once every 5 years. It's a Gauss's law problem that involves you figuring out how much charge is enclosed when you are sitting at a point inside a charged sphere. I would recognize how to do that if I were you. I don't really believe that the first portion of the problem is all that tough. However, this is a problem where you have to use this to create an expression for the electric potential. And remember, the electric potential assumes you're dealing with how much energy was necessary to move a particle from far away to a point that's going to be closer, in this case, inside the charge of the sphere. We talked about this a while ago, but I kind of want to point it out. The electric field looks something like this. As we talk about, how much electric field is around this charged insulator. The electric field increases, you get closer, and then as we start to penetrate inside, because you've got this charged shell around you that's insulating you a bit from the charge that's inside, or charge that's around the outside of the cube, or outside of the sphere, the electric field slowly goes to 0 as you get closer to the center. Because by the time you make it to the center, you have equal amounts of charge all around you. So this idea that the electric field is linear at this point inside of the radius of the sphere and is 1 over distance squared means that outside you can treat it like it's a point charge, but inside you can't. What's not obvious, and I think this is important, so a lot of people think that the electric potential should have some kind of similar look to it. but it won't. The electric potential is going to do exactly what you expect. It's going to get harder and harder and harder and harder to reach the surface of this thing. But there's still more electric field pushing you away as you try to get inside. So it's going to continue to become more and more difficult to get to the center of the sphere. Because while you're inside the sphere, the electric field is still trying to push you away. It takes more work to push that charge through the sphere and get to the center. The electric potential is about work. But the electric field is about charge. So in calculating the electric field, you use Gauss's law, which is about how much charge is inside your surface. But the electric potential isn't. So you can't use this to determine the electric potential from a system like this. You can do so in some circumstances where you have a charged object, but if you want to get inside the object, like we do in this case, you can't use this. At least not, I don't know of a good mathematical way to use this, because you're inside the object. So the best way to go is to use that function. Now, here's the next thing. The electric potential is a summation. This next part may or may not make sense to some of you. And so I'm not going to spend a huge ornament of time like convincing you of this. We have all year to continue to convince you of this. Part A, I think, is pretty straightforward in that we have an expression for the electric field outside of our charged sphere. And it's going to behave just like a point charge. So if I did this, let me write this different, just so I remind myself that we have to go back and talk about something. This is kind of what we did already once, to talk about the electric potential for a point charge. And I say kind of, it's exactly what we did. We just went to a distance that was somewhere outside of our point charge. This time I'm making that distance all the way to the surface of the sphere. Now, once we get there, that's the amount of potential energy required to get to that point. If I want to continue, if I want to find out how much more potential energy is required to move inside the sphere, I need to add to this amount of energy that I took to get here. And I know I keep saying potential energy, but remember, this came from a derivation about potential energy. So I think I'm okay using that reference. We've just divided out the charge that was used to go from infinity to here. So if I want to find the electric potential inside the sphere, I still have to take as my point of reference a place at infinity. I still have to start from there, because I have to deal with all the energy it took to get to the surface, and now the additional energy it takes to get inside. And for those of you who haven't yet recognized, these are notes. These are not how to solve the problem. This is something you need to know. And I'm not sure you would have known it on your own. It was said in class, but that doesn't necessarily mean it's something that you would have known on your own. So if I actually want to find the electric potential for a point inside the sphere, say here, a distance, I'm going to use x away just to give myself another variable away from r. I could say that would be what I would need to do. That I would have to take the electric potential as an integral from a place at infinity to a place at distance x away. But there's two different expressions for the electric field. One when I'm outside the sphere and one when I'm inside the sphere. Because of that, and because it's a simple sum, I'd have to break this up into two intervals, two different sums. One for the expression of the electric field outside the sphere, and one for the expression of the electric field inside the sphere. I'd have to calculate the work done to get to the surface, and then the work done to go inside. Yes, sir?
For the second integral, shouldn't the top limit be bigger?
Oh, I'm sorry, yes. Yeah, to get to the surface of the sphere, then from the surface to a place inside. Now, in calculating these, there's an issue that we will have to discuss, and I'm not going to discuss it today, but it has to do with that negative sign I told you was an issue before, and we're going to have a conversation about it. But for right now, based on the time, and I don't want to cause any extra due confusion, this will still do the job. Now, we already have an answer for this. You don't have to do this again. The electric potential to get to the point on the outside edge of the sphere is Q over 4 pi epsilon naught R. We treat it like a point charge up until we're at the edge of the sphere. So that's not a calculation that you have to worry about. The only thing that is a calculation you have to worry about is this portion. That's the part that matters. So that's the only thing that you had to do new in this problem. And we're going to be adding up that amount. Now, I would like you guys to do this. Not this minute, but once you have this here, I would like you guys to try it on your own time and see what happens. Because I want to talk about question 9 too. And I want to have time for that. So, question 9 is a perturbation on this. And so, if you haven't read question 9, I believe it's a point charge, but then there's a solid conducting sphere placed around the outside of the point charge. Is that right?
I think it's the inside.
Yeah, it's not a point charge, it's just an insulated sphere on the outside.
Yeah.
All right. So it's the same thing we just did. So I still feel I'm not adding much because you already did the point charge problem. You already did this problem. So the reason why I think you should look at this question too is everything you've just done in the service of doing the problem that we just talked about. It's very similar here. And there's probably some inner and outer radius stuff that I gave. I don't know what they are, but maybe A and B.
Yep.
Is that true? Okay. When we put this conductor here, something special happens with the conductor, and it warrants at least a slight conversation. We know that if there's a conductor there, the electric field inside the conductor is 0, which means by definition, no work will have to be done going from the outside of the conductor to the inside of the conductor. The electric field is 0, But that doesn't mean the electric potential is 0. Now, the electric potential inside the conductor has got to be constant. That makes for a weird answer. And we really can't talk about it until you guys have done a little bit of practice to get here. I want you to think for just a minute. I'm hoping that at least a few of you can follow along and note that the electric potential at the surface of the conductor has to equal this value. Is everybody okay with that? This is the equation for an electric potential outside of a charge, assuming that we started that charge from a place at infinity and moved to a place that was a distance b away from the charge. So from infinity to right here at the surface. Everybody okay so far? There's probably a group of people who think the electric potential here would be V over Q times 4 pi epsilon naught A. But it's not. And here's where you have to come to an understanding that is different than what you believe, or at least different than what I've taught so far. This relationship right here assumes the same electric field existed in space from infinity to point B. It assumes the entire time the electric field was somehow proportional to your distance away from the charge. That's what it assumed. But inside this space, there's no electric field. So the electric field here, the electric potential here has to be the same as the electric potential there. Which means that if this is at the outer surface B, when we go to the outer surface A, the electric potential is still the same value as it was on the outside surface because the electric field is 0 inside the conductor. Meaning the white line represents the electric potential if there was no conductor there at all. And I was able to go from infinity all the way to the surface of that sphere. But if I place the conductor there, the moment I get to B, going from B to A, there would be no change in electric potential. And from here, I would start doing the same amount of work as before, but now I started with less electric potential. So it wouldn't increase to be as high. So this, I guess I should have made this a different color. This separation occurs because no work was done while I was inside the conductor. So the total amount of work done to get to the surface of the sphere has to be less by the time I get to that sphere. Because for the time that I was inside the conductor, no work was done. Eight and 9, I think, have a lot to take in. Okay, Jeremy. If we want to know what the change, let me write it all out again, sorry. If we want to calculate this portion of the electric potential, get an expression or get a value, then we use this function. And we know what the electric field is inside the conducting sphere. We know that that's going to be Q over 4 pi epsilon naught R. There, like that. And we're going to do this from A to, say, the surface of the sphere. Now, this is just going to get us a value for how much the potential changed from A to R. So this no longer equals the electric potential. This equals the change in potential from A to R. And this would only have been the electric potential if it had started from a place where the potential was 0 at our starting location, and this one doesn't. This change in potential is starting at a place where we already have a potential. So this delta V would eventually have to be replaced with V at R, which is what we are solving for, minus V at A, which we already know to be Q over 4 pi epsilon naught B. And then that would equal the result of that huge integral, which is not a huge integral, but still. Now this is a lot to take in. And don't worry, this is not on your test. I think this is something we should probably revisit 4 or 5 times throughout the course of the year, because this is a lot. And I don't hold any illusion that this is probably way over the top for some of you. This is the absolute craziest stuff. But it's an understanding about the difference between electric potential difference, and the work that is different between those two. The electric potential, when you say I'm giving you the electric potential at a point, you are suggesting that you took that measurement relative to a place where the object had no energy when you started. You were really far away. So the absolute electric potential starts someplace where you are not interacting with the object. Potential difference, you can take that from anywhere, but you will need to know where your potential started and where your potential ended up. And you may not be able to count that the way you think you can. But you do this problem, you're going to get the change in potential as noted. By the way, when you do this, you're going to get the result that you, I'm sorry, I have a mistake. Nobody pointed it out, thank you, but I wish you had earlier. So I've been supposed to be putting the electric field in for this, and the electric field is R squared. Sorry, fix it right now, please. Don't have it bad in your notes. If you wrote any notes down that involved this, inside that integral should have been R squared every time. Anytime it's inside the integral. I think just here. Now, we know the result of this integral is still going to be Q over 4 pi epsilon naught times R. And then you're going to plug in your value of A and capital R. That's still going to be true. It's just that this will be a change in potential from A to the surface of the sphere. But it still starts with this much potential before we even begin the integral. 8 and 9 were tough. 8 and 9 were tough. I mean, I don't have a problem with it. Some of you need to grapple with the hard stuff. I'd argue that 1 through 7 weren't so tough. They got progressively harder. I think question 7 was interesting. How many of you did the ring question? Not terrible? Certainly easy with the electric potential. The electric field, a little more difficult because you had to scale it for direction. But you can check your work pretty easy, because if you put in 0 for Z, it should become pretty obvious that your answer matches up with what you get for the first part of 7. And if it doesn't, you did it wrong. Anyways. This gives you the wrong answer. Part of the reason Bohr knew that they were wrong, and why people like Schrödinger and Planck and Heisenberg and de Broglie, they all had different ideas of what was happening. The ionization energy we get here is based on the classical concept that there's a proton and an electron. They are attracted to each other. And that force of attraction contains a certain amount of energy. And for you to ionize the atom, you have to take the electron and move it to a place that's infinitely far away. So that amount of energy is just calculating this. The proton is a point charge. We are bringing a electron close to it and forming the atom. That's the amount of energy that will exist in this pairing. Now, the difference is the amount of potential energy here works out to be negative because it's bonded together. You have to add energy to separate the electron. But if we're just looking for the magnitude of the energy, we just need to figure out what Q times V is. You needed to look something up, though, in order to do this problem. You needed to find out what the Bohr radius was. I'm sure even the little internet could have given you the size of the Bohr radius. You could have used the big internet, but I think if you type in Bohr radius, you'll have this separation distance, which is what, like 5 times 10 to the negative 11th? I don't have the decimal part. I can't hear you. 5.3 times 10 to the negative 11th meters. So all I did is say, okay, the electron is charge E. The proton is charge E. So this is what I was going to use to calculate it. I did it 2 different ways, just for, I don't know, just because I wanted to compare it to something else. If you calculate this, your answer comes out to be volts. And then if you multiply by coulombs, you get joules, because a volt is a joule per coulomb. But if you leave that answer in terms of volts, you get an answer that's in terms of EVs, electron volts, which was worth doing for me because I wanted to compare it to the known value for the ionization energy of a hydrogen atom, which is almost always expressed in electron volts. But if you went ahead and plugged in the value of the charge, which you could have, then you would have gotten the value in joules. So I plugged all the numbers in, and let's see, what did I get? I got 27 electron volts and 4.36 times 10 to the negative 18th joules. The actual ionization energy for hydrogen is 13.5 electron volts. So this is actually more energy than is required to ionize a hydrogen atom. There's a lot of reasons for that. You guys who have had any amount of chemistry, because now that I teach chemistry, I know things, should know that the electron structure is not a bunch of little things orbiting planets like, people tend to think. But it's interesting to note that it's less than the predicted amount. Part of the reason is the electron can't exist in all of those spaces in between. You can assume that you go from the 1s shell to the 2s shell. The electron doesn't exist anywhere in the middle. Because of that, no work is done going from one of those shells to the next. It's like an electric field of 0 between those two. So if you're taking an electron all the way off the atom, all the spaces where the electron can't exist would be like a conductor, and no work is done removing it. So, bless you.